Look at the screen and imagine descending into the absolute darkness of the ocean. As the sunlight fades into a permanent midnight, the rules of biology begin to warp in ways that defy human imagination. In the shallow waters, animals remain bounded by predictable sizes, limited by the fierce competition of common ecosystems. But thousands of meters beneath the surface, where the water temperature hovers just above freezing and the pressure is powerful enough to crush a military submarine, a bizarre evolutionary phenomenon occurs. This is the realm of deep-sea gigantism, where ordinary creatures are transformed into towering titans of the abyss. Woodlice that are usually the size of a coin on land expand into heavy armoured beasts the size of a cat. Delicate crabs stretch their legs out to a terrifying span of 4 meters. Squids, which we usually see as small and agile, become gargantuan monsters that match the length of a transit bus. Why does an environment defined by extreme scarcity, absolute darkness, and crushing force produce the largest invertebrates on Earth? Today we will explore why deep-sea creatures become giants. This structural transformation is not a random mutation, but a calculated survival mechanism dictated by the laws of physics, chemistry, and slow-motion metabolism. We will dissect the exact reasons behind this biological marvel. If you find this journey into the deep ocean fascinating, please hit the like button and subscribe to the channel to support our research. Before we dive into the deep physics of the abyss, please leave a comment below sharing exactly where in the world you're watching from and what time it is right now in your location. Now, let us begin our journey down into the crushing darkness. To truly comprehend why the deep sea produces creatures of such monumental proportions, we must first strip away our terrestrial biases and analyse the unforgiving physical architecture of the abyss. The deep ocean is not merely a dark version of the surface, it is an entirely different thermodynamic and mechanical universe. 2 primary physical variables govern every cubic centimetre of this space: extreme hydrostatic pressure and near-freezing thermal stability. To any land-dwelling organism, these conditions represent instant death. Yet, to the titans of the deep, they are the very sculptors of their giant forms. Let us first examine the relentless force of hydrostatic pressure. On land, human beings and other animals live under 1 atmosphere of pressure, which is roughly 1 kilogram of force per square centimetre of our bodies. We do not feel it because our internal pressures are equalised with the outside air. However, as you descend into the ocean, the weight of the water column above you piles up with terrifying speed. For every 10 meters of depth, the pressure increases by 1 full atmosphere. By the time you reach a depth of 1,000 meters, the pressure is 100 times greater than at the surface. At the average depth of the ocean floor, around 4,000 meters, the pressure reaches 400 atmospheres. This is equivalent to having an elephant standing on your thumb, or a total force of several tons pressing down on every square inch of an organism's surface. For many decades, scientists believed that such extreme pressure would completely pancake any living tissue, making life, let alone giant life, utterly impossible. But physics operates differently when an organism is properly engineered. The secret lies in the fact that water is virtually incompressible. If a creature's body is composed primarily of water and lacks any air-filled spaces like lungs or swim bladders, the internal pressure of the creature's cells will perfectly match the external pressure of the ocean. There is no crushing force because there is no empty space to crush. The pressure inside equals the pressure outside. However, this creates a major molecular challenge. While the macrostructure of the animal does not implode, the extreme hydrostatic pressure behaves like an invisible vice at the microscopic level. It packs molecules closer together, which directly interferes with the flexibility of cellular membranes and the functionality of crucial proteins. Under hundreds of atmospheres of pressure, the lipid bilayers that form the walls of cells become rigid, turning from a fluid, flexible state into a stiff, gel-like state. If a cell membrane becomes too stiff, it can no longer transport nutrients in or waste products out. Furthermore, proteins, which must change shape to catalyze chemical reactions and sustain life, find themselves locked in place by the immense weight of the surrounding water. To counteract this molecular immobilization, deep-sea giants have evolved unique biochemical adaptations that directly influence their physical structure. They fill their cells with specialized compounds known as piezolites, most notably trimethylamine oxide, which acts as a molecular stabilizer. This compound binds tightly to water molecules, creating a protective hydration shell around proteins and cell membranes. This shell prevents the immense pressure from distorting the shape of the proteins or forcing the cell membranes to solidify. Interestingly, research indicates that the concentration of trimethylamine oxide in marine organisms increases linearly with depth. The deeper a creature lives, the more of this stabilizer it needs. This molecular reality links directly to the physical necessity for larger size. In a highly pressurized environment where cell membranes are structurally reinforced and stabilized by heavy concentrations of compounds like trimethylamine oxide, the overall metabolic cost of maintaining cellular integrity increases. To optimize this energy expenditure, evolution favors an increase in overall cell volume and a reduction in the surface area to volume ratio of the organism. By growing larger, a creature reduces the relative amount of surface area exposed to the harsh external environment while maximizing its internal volume. A larger body can house larger, more stable cellular networks that operate with greater mechanical efficiency under the immense weight of the water column. Now, let us overlay the second great physical variable of the deep sea, the profound, unchanging cold. Beyond the reach of the sun, below the thermocline layer where water temperatures drop precipitously, the deep ocean settles into a permanent state of near-freezing chill. Across the global abyss, the temperature remains remarkably constant, hovering between 1 and 4 degrees Celsius. Unlike the surface waters, which experience drastic fluctuations based on seasons, weather, and latitude, the deep ocean has maintained this icy stability for millions of years. This extreme cold has an immediate and powerful effect on the fundamental laws of thermodynamics within a living organism. According to the principles of chemical kinetics, temperature is a direct measure of kinetic energy. In a cold environment, molecules move more slowly, chemical reactions lose their speed, and diffusion rates drop significantly. For a cold-blooded organism whose internal body temperature matches the surrounding water, this means that every single biological process slows down to a crawl. This thermal reality brings us to one of the most foundational principles in biogeography, Bergmann's rule. Formulated in the 19th century by biologist Carl Bergmann, this ecological principle originally stated that within a broadly distributed taxonomic clade, species of larger size are found in colder environments, while species of smaller size are found in warmer regions. While Bergmann originally applied this rule to warm-blooded animals, noting that a larger body retains heat better due to a smaller surface area to volume ratio, the rule has been observed to apply spectacularly to cold-blooded ectotherms in the ocean depths, a phenomenon known as polar and deep-sea gigantism. In the freezing depths, the mechanism driving Bergmann's rule shifts from heat retention to energy conservation and cell efficiency. When temperatures are low, the rate of cellular division slows down dramatically, but the growth of the individual cells does not stop at the same rate. This leads to a biological phenomenon known as the temperature size rule, where organisms reared in cold temperatures grow more slowly but ultimately reach a larger adult size than their warm water counterparts. The cold water forces cells to grow larger before they divide. Consequently, the entire structural blueprint of the animal expands, resulting in tissues and organs that are physically larger from the day of birth. Furthermore, the physical state of the water itself changes at low temperatures. Cold water is significantly more viscous than warm water. This means that moving through near-freezing water requires more physical effort, because the water feels thicker and offers more resistance to a swimming creature. For a tiny organism, this high viscosity is an immense barrier. It feels like trying to swim through syrup. Tiny appendages struggle to create propulsion, and the energetic cost of movement becomes unsustainably high. However, as an organism increases in physical size, the laws of fluid dynamics shift in its favour. In physics, this is described by the Reynolds number, a dimensionless quantity that helps predict flow patterns in different fluid situations. At low Reynolds numbers, which apply to small organisms, viscous forces dominate, making movement highly inefficient. At high Reynolds numbers, which apply to large organisms, inertial forces dominate. By evolving a giant physical form, deep-sea creatures successfully break through the viscous barrier of the cold water. Their massive bodies possess enough inertia to glide through the dense cold currents with minimal effort, saving vast amounts of energy over their lifetimes. The combination of extreme pressure and low temperature also alters the physical properties of the materials that deep-sea creatures use to build their bodies. Consider the construction of a skeleton or a protective shell. In shallow, warm waters, marine organisms easily extract calcium carbonate from the ocean to build thick shells and sturdy bones. But as pressure increases and temperature drops, the solubility of calcium carbonate changes drastically. Under the physical conditions of the deep sea, calcium carbonate becomes highly soluble and begins to dissolve. This boundary is known as the carbonate compensation depth. Below this depth, it becomes physically and energetically exhausting for an organism to maintain a heavy, calcified shell or a dense, bony skeleton. The environment is actively trying to dissolve their structural support. To survive this physical constraint, deep-sea giants have abandoned heavy, brittle armour. Instead, they utilize alternative structural engineering. Many deep-sea crustaceans and invertebrates replace calcium carbonate with chitin mixed with flexible proteins, or they allow their structures to become soft, gelatinous, and highly hydrated. This lack of heavy, restrictive skeletal frameworks creates a physical freedom that is completely absent in shallow water species. Without the burden of carrying a massive heavy shell and freed from the structural limitations imposed by gravity, thanks to the natural buoyancy of water, there is no immediate physical ceiling preventing these creatures from expanding outward. A land animal that grows too large will eventually be crushed under its own weight because its bones cannot support the mass. In the deep sea, the buoyant force of the dense, cold water completely neutralizes gravity, while the fluid-filled, non-calcified tissues adapt perfectly to the ambient hydrostatic pressure. The physical constraints that limit size on land and in shallow water are dismantled in the abyss. Thus, the physics of the deep sea creates a perfect storm that drives the evolution of giants. The extreme pressure demands large, stable cell volumes and low, surface area to volume ratios to maintain cellular integrity. The freezing temperatures slow down cell division, allowing individual cells to grow much larger before replicating, while simultaneously increasing water viscosity to a point where only massive bodies can move through it efficiently. Finally, the dissolution of calcium carbonate eliminates the possibility of heavy armour, encouraging the growth of flexible, highly hydrated and unconstrained body plans. When we gaze into the abyss, we are looking at an environment where the laws of physics do not restrict size but rather mandate it. Gigantism is not a luxury or a freak accident of nature. It is the ultimate mechanical and physical solution to surviving a world of maximum pressure and absolute cold. Every millimetre of a deep-sea titan's body is a direct reflection of the immense physical forces that push down from miles above, carving out a realm where the small perish and the giants rule supreme. Moving beyond the raw mechanics of physical force and temperature, we must investigate the chemical landscape of the deep ocean. To understand the immense scale of deep-sea giants, one must solve a profound chemical puzzle. In the terrestrial world, areas of extreme cold and low energy are typically associated with stunted growth and sparse biological development. Yet, the deep ocean floor breaks this rule entirely. The secret to this biological anomaly lies deep within the molecular chemistry of seawater, specifically revolving around a phenomenon known as the oxygen paradox. To understand how this chemistry fuels gigantism, we must look at the behaviour of gases dissolved in liquids. On the surface of the Earth, warmer temperatures generally accelerate chemical processes and promote active life. However, when it comes to the retention of gases, the laws of thermodynamics reverse this dynamic. The solubility of a gas in water is inversely proportional to the temperature of that water. In warm surface waters, molecules move with high kinetic energy, making it easy for dissolved gases to escape the liquid phase and evaporate back into the atmosphere. Conversely, as water cools, its molecules lose kinetic energy and pack more tightly together. This slow, molecular movement creates a stable liquid matrix that can trap and hold on to gas molecules with incredible efficiency. Because the deep ocean is filled with water that hovers just above the freezing point, its theoretical capacity to hold dissolved oxygen is vastly superior to that of tropical or temperate surface waters. But this physical capacity raises an immediate question. How does that oxygen get down into the dark abyss in the first place, miles away from the photosynthetic plants and atmosphere that produce it? The answer lies in the global conveyor belt of ocean currents, known as thermohaline circulation. This chemical transport system begins in the polar regions, primarily near Greenland and Antarctica. In these icy zones, surface water becomes extremely cold and highly saline due to the formation of sea ice, which leaves salts behind in the remaining liquid water. This combination of low temperature and high salinity makes the water incredibly dense. Before this polar water sinks, it is exposed to the howling polar winds, saturating it with atmospheric oxygen to the absolute point of chemical equilibrium. Once fully charged with oxygen, this heavy cold water plummets into the depths of the ocean, creating massive subsurface rivers known as deep water masses. These deep currents slide along the ocean floor, travelling thousands of miles from the poles into the Atlantic, Indian and Pacific basins. This means that the water filling the deep ocean trenches is not stagnant or depleted. It is a highly oxygenated current delivered directly from the poles. By the time it reaches the abyss, this water contains a much higher concentration of dissolved oxygen than almost any warm surface environment on Earth. This abundance of oxygen creates a striking chemical contrast with the surrounding environment. While the deep sea is severely starved of food and energy, it is completely saturated with the primary fuel needed for cellular respiration. This is the foundation of the oxygen-rich gigantism hypothesis. In basic biology, oxygen is the ultimate electron acceptor in the process of aerobic metabolism. It allows cells to break down organic molecules and convert them into adenosine triphosphate, the universal energy currency of life. When oxygen is scarce, organisms must rely on less efficient anaerobic pathways, which limit energy production and restrict maximum body size. But when oxygen is abundant, cells are freed from these chemical limitations. At the cellular level, the sheer availability of oxygen molecules shifts the physiological boundary of what a cell can achieve. Because the water is freezing cold, the metabolic rate of a deep-sea creature is naturally low, meaning its cells consume oxygen at a very slow pace. When you combine an incredibly low consumption rate with a massive, highly concentrated supply of dissolved oxygen in the surrounding water, the internal oxygen tension within the animal's tissues remains exceptionally high. This high oxygen availability directly alters the physical constraints of oxygen diffusion. For any animal, oxygen must travel from the environment across a respiratory surface like gills or skin and diffuse through tissues to reach individual cells. According to Fick's laws of diffusion, the rate of gas transfer is directly proportional to the concentration gradient between the outside environment and the inside of the organism. In warm or poorly oxygenated water, this gradient is shallow, meaning oxygen struggles to penetrate deeply into thick, dense tissues. This physical law forces shallow water organisms to develop highly complex, energy-consuming circulatory systems, or it forces them to remain small so that oxygen can easily reach their core. In the deep sea, the massive concentration gradient eliminates this barrier. Oxygen molecules are forced into the organism's body by sheer chemical pressure. Because oxygen diffuses so effortlessly through the tissues under these conditions, it can travel much greater physical distances before being completely consumed by metabolic processes. This simple chemical shift removes the biological ceiling on tissue thickness and body volume. An organism can grow thicker muscles, larger organs, and a vastly expanded overall body mass because it does not need to worry about its inner cells suffocating from a lack of supply. This chemical freedom is most visible when we look at polar and deep-sea invertebrates, many of which lack complex circulatory systems altogether. Consider creatures like giant sea spiders or massive marine isopods. In warm waters, their relatives must stay tiny because they rely entirely on simple diffusion across their outer body surfaces to breathe. If a shallow water sea spider grew to the size of a dinner plate, its internal tissues would rot from oxygen starvation because the gas could not diffuse fast enough to keep up with its warm metabolism. But in the deep, icy abyss, the combination of a slow-motion metabolism and high oxygen concentrations allows these exact same primitive body plans to expand to monstrous proportions. The oxygen simply permeates through their entire structure, fueling large cells located deep within their giant bodies without requiring a complex network of blood vessels. Furthermore, this rich chemical environment alters the very structure of the cells themselves. Under high oxygen availability and low temperatures, cells do not divide as rapidly, but they accumulate greater amounts of structural proteins and lipids. The individual cellular building blocks of deep-sea giants are often significantly larger than the cells of corresponding shallow water species. This cellular enlargement, known as hypertrophy, directly contributes to the macro-scale gigantism of the entire organism. The animal is not necessarily made of more cells. It is made of larger, structurally robust cells that are continuously bathed in an optimal chemical soup of dissolved oxygen. This abundance of oxygen also interacts uniquely with the chemical composition of deep-sea water regarding waste management and metabolic efficiency. In a warm environment, rapid metabolism generates high amounts of metabolic waste products, such as lactic acid and carbon dioxide, which must be rapidly cleared from the body to prevent cellular toxicity. In the deep sea, because the chemical reactions are slowed by the cold, the production of these toxic byproducts is drastically reduced. The organism operates with extreme chemical cleanliness. Every molecule of nutrients it manages to capture is processed with maximum efficiency, leaving almost no chemical residue that could disrupt cellular function. This pristine chemical balance allows deep-sea giants to dedicate almost all of their limited resources to structural maintenance and steady, long-term growth. Instead of burning energy to pump blood furiously or clear metabolic toxins, their bodies can use their resources to slowly build up massive frameworks of tissue. The high oxygen levels guarantee that even at large sizes, every single cell maintains an optimal energetic state, protected from the stress of hypoxia. Thus, the chemistry of the deep ocean turns the traditional rules of ecology upside down. The abyss presents a unique environmental paradox. It is an ecosystem with almost nothing to eat, but with an endless supply of the clean chemical fuel needed to process that food. It is this specific chemical asymmetry that makes deep-sea gigantism possible. Without this polar-driven pipeline of cold, highly oxygenated water, the extreme physical pressures and structural demands of the deep sea would simply result in a barren wasteland of microscopic life. Instead, the chemistry of the deep transforms the dark waters into a breeding ground for giants, providing the molecular foundation that allows simple cells to expand outward, breaking through standard biological limits to construct the largest, most enigmatic creatures on our planet. Having analysed the physical force and chemical framework of the deep sea, we must now delve into the complex machinery of life itself. Metabolism. In the shallow, sunlit portions of the ocean, energy flows abundantly. Microscopic plants capture sunlight, converting it into a massive base of organic matter that fuels rapid life cycles, swift movements, and high metabolic rates. But as you drop past the twilight zone and enter the true abyss, this energy pipeline collapses. The deep ocean is characterized by severe permanent starvation. Less than 1% of the organic material produced at the surface ever manages to drift down to the ocean floor. To survive in this biological desert, creatures cannot afford to live fast. They must master the art of the slow-motion economy, and counterintuitively, the primary weapon they use to conquer this extreme famine is massive physical size. To understand this energetic paradox, we must look at a fundamental principle of comparative physiology known as Kleiber's law. Formulated by the biologist Max Kleiber, this law describes the mathematical relationship between an organism's total body mass and its metabolic rate. It states that an animal's metabolic rate scales to the 3/4 power of its body mass. In simple terms, as an organism grows larger, its total energy consumption does increase, but its specific metabolic rate per gram of tissue drops dramatically. A large animal operates with vastly greater energetic efficiency than a small animal. Consider the difference between a mouse and an elephant on land. A mouse must consume its own body weight in food every few days because its tiny body loses heat rapidly, and its cells burn through energy at a frantic pace. An elephant, despite its colossal size, burns energy at a much slower relative rate per cell, allowing it to survive on lower quality food processed over a longer period. In the freezing, food-starved depths of the ocean, this scaling law becomes a strict rule for survival. By evolving a giant body, a deep-sea creature drastically reduces the energetic cost of maintaining each individual gram of its living tissue. A giant isopod, or a colossal squid, is essentially an ultra-efficient energy-saving machine, engineered to extract the maximum possible lifespan out of every single calorie it consumes. This metabolic slowdown is further amplified by the extreme cold we discussed earlier. Because these creatures are ectothermic, their internal biochemical clocks are synchronized with the near-freezing ambient water. Enzymatic reactions occur at a fraction of the speed seen in warm water species. Their cellular engines do not roar, they idle at the absolute minimum threshold required to sustain life. Nerve impulses travel more slowly, heartbeats are separated by long intervals of silence, and muscular contractions are deliberate and measured. This state of low metabolic demand means that a deep-sea giant requires a surprisingly small amount of food to maintain its basic physiological functions. However, reducing energy expenditure is only half of the survival equation. The other half is managing the unpredictable arrival of food. In the deep sea, meals do not arrive daily. There are no vast schools of bait fish or predictable seasonal blooms of plankton. Instead, the ecosystem relies on chance events. The primary food sources are marine snow, a continuous but low-nutrient drizzle of dead organic flakes, fecal pellets, and mucus from above, and marine falls, which are the sudden, catastrophic drops of massive carcasses such as dead whales, large sharks, or giant pelagic fish. When a whale dies at the surface, its massive body sinks through the water column until it impacts the abyssal plain, a phenomenon known as a whale fall. In an instant, a single spot on the barren seafloor is gifted with several tons of highly concentrated protein and lipids. This event creates a localized oasis of life in the desert. But these events are exceptionally rare, separated by vast distances of empty water and unpredictable spans of time. A creature living on the seafloor might have to wait months or even years between major feeding opportunities. This is where the evolutionary strategy of gigantism reveals its true brilliance as a survival mechanism. A large body acts as a massive biological storage battery. When a deep-sea giant encounters a food source like a whale fall, it can consume immense quantities of nutrients far beyond its immediate operational needs. Their digestive systems and internal tissues are designed to expand and store these resources. Because their baseline metabolic rate is so incredibly low due to Kleiber's law in the cold water, these stored nutrients are depleted at an exceptionally slow pace. A prime example of this can be seen in giant isopods. These creatures can gorge themselves on a carcass until their segmented exoskeletons distort. packing away enough fat and protein to survive for multiple years without another single bite of food. A small crustacean, operating with a higher relative metabolic rate and lacking the physical capacity to store massive energy reserves, would burn through its internal resources within weeks and starve to death long before the next carcass drifted down from the surface world. Beyond simple storage capacity, a large body provides a massive advantage in locomotive efficiency, which is critical for locating these sporadic food oases. In the deep ocean, finding food requires crossing vast expanses of empty territory. If an animal is small, its locomotion is highly limited by its physical dimensions. It can only cover a small area each day, and it expends a high proportion of its limited energy simply fighting the natural friction of the water. A large animal, however, possesses longer limbs, larger fins, or more massive muscular structures that allow it to cover vast distances with minimal strokes. Because of their mass, these giants possess immense physical inertia. Once they initiate movement, they can glide through the water column, utilizing their momentum to travel kilometers of dark ocean while expending very few calories. This allows them to effectively patrol much larger territories, vastly increasing their mathematical probability of intercepting a falling carcass or locating a hydrothermal vent ecosystem. Gigantism turns a blind search in the dark into an efficient, wide-ranging scouting operation. Furthermore, the mechanics of starvation survival favour large organisms in terms of tissue composition. When an organism goes without food for an extended period, its body must eventually begin to break down its own tissues to provide energy for vital organs like the nervous system. In a small creature, the margin of safety is razor thin. It possesses very little non-essential tissue, meaning that structural degradation quickly leads to organ failure and death. Deep-sea giants, by contrast, often develop body compositions that double as functional energy reserves and buoyancy aids. Many of these animals possess vast stores of low-density lipids, oils, and watery connective tissues throughout their frames. When famine strikes, they can slowly metabolize these non-critical structural components over vast stretches of time without compromising their core biological functions. They can literally shrink or utilize their internal reservoirs while waiting out the resource drought, a luxury that a small organism simply cannot afford. We must also look at the competitive dynamics that occur when food does arrive. When a whale fall or a large fish carcass hits the seafloor, it sends a chemical scent plume travelling through the deep currents. Within hours, predators and scavengers from miles around begin to converge on the site. In this crowded, high-stakes environment, physical size dictates the hierarchy of consumption. A giant creature can easily intimidate, displace, or simply out-eat smaller competitors. They can shield a food source with their physical mass, preventing smaller organisms from accessing the premium portions of the carcass until the giant has satisfied its needs. In the brutal economy of the deep, being the biggest animal at the feast ensures that you get the lion's share of the energy, further reinforcing the metabolic cycle that allows you to maintain that giant size in the first place. This relationship between size, starvation, and metabolism reshapes our understanding of evolutionary success. In warm, shallow waters, evolution often rewards speed, agility, and rapid reproduction. Animals compete by being faster than their prey and quicker than their rivals, a lifestyle that requires a massive continuous intake of calories. In the deep sea, that lifestyle is a recipe for rapid extinction. The deep sea does not care about speed, it rewards endurance. Gigantism is the ultimate manifestation of evolutionary endurance. It is a highly sophisticated physiological strategy where the organism trades rapid development and high activity levels for massive structural stability, long-term energy storage, and unparalleled metabolic efficiency. By growing into a titan, the creature effectively detaches itself from the daily panic of finding food. It transforms itself into a slow-moving, long-enduring monument of biological engineering, capable of drifting through the cold, crushing dark for years on end, waiting with infinite patience for the next drop of energy to fall from the world above. The giants do not survive despite the starvation of the deep sea. They are large precisely because it is the only way to beat the hunger. To truly uncover the secret of deep-sea gigantism, we must examine a dimension of biology that is often invisible but completely revolutionary: time. On the surface of our planet, life moves at a frantic, hurried pace. Organisms are bound by the volatile cycles of changing seasons, shifting climates, and the constant threat of active, fast-moving predators. This chaotic environment forces surface species to grow quickly, reproduce early, and consequently age and die within a relatively short span of time. But as we cross the threshold into the deep ocean abyss, the concept of time stretches and warps. Here, we encounter an environment of absolute, unchanging stability, where the standard processes of biological aging slow to a near-complete halt. This profound temporal distortion allows deep-sea creatures to live not just for decades, but for centuries, giving them an unprecedented window of opportunity to continuously expand their physical bodies into staggering proportions. Let us first examine the unique structural stability of the deep-sea environment. The abyssal plain is perhaps the most predictable ecosystem on Earth. At depths below 2,000 meters, there are no storms, no heat waves, no winters, and no sudden disruptions in habitat. The temperature remains locked in a permanent freeze of 1 to 4 degrees Celsius, century after century. This total absence of environmental volatility removes a massive source of physiological stress from the organisms that dwell there. On the surface, animals must constantly expend energy adjusting to fluctuations in temperature, humidity, and food availability. This constant adaptation causes cellular wear and tear, accelerating the aging process. In the abyss, the biological machinery of a creature operates in a flawless, unchanging laboratory environment. This environmental stillness allows for an extraordinary reduction in what scientists call the baseline rate of cellular damage. To understand aging, we must look at the mitochondrial engines inside cells. As cells convert nutrients into energy, they inevitably produce unstable, oxygen-bearing molecules known as free radicals or reactive oxygen species. In warm-blooded animals or fast-moving surface organisms, the rapid burning of energy creates a torrent of these free radicals. These volatile molecules bounce around the interior of the cell, crashing into delicate structures, damaging cellular membranes, and causing mutations in deoxyribonucleic acid. Over time, this cumulative damage degrades the functionality of tissues, leading to senescence, aging, and eventual natural death. In the deep sea, this destructive process is entirely neutralized by the combination of freezing cold and slow metabolism. Because the internal chemical engines of deep-sea ectotherms idle at such a low rate, the generation of reactive oxygen species drops to an absolute minimum. The cells do not suffer from the fiery, chaotic oxidation that ravages surface animals. Instead, their cellular components remain pristine, operating with minimal molecular friction. The structural integrity of their proteins, lipids, and genetic material is preserved for durations that seem impossible by human standards. Furthermore, deep-sea organisms have evolved highly advanced, slow-acting genetic repair mechanisms that take full advantage of this low-friction lifestyle. Because they are not rushed by the need to grow quickly before a change in seasons, their cells can dedicate vast amounts of time to quality control. When a strand of deoxyribonucleic acid is damaged, or a protein is misfolded, the cell does not rush past the error to continue dividing. Instead, it carefully dismantles and repairs the damaged component, ensuring that the cellular architecture remains entirely error-free before proceeding with slow replication. This flawless quality control at the microscopic level prevents the onset of genetic degradation, effectively turning off the biological countdown clock that dictates aging. This cessation of typical aging brings us to a crucial concept known as indeterminate growth. Most terrestrial animals, including humans, mammals, and birds, exhibit determinate growth. We possess genetic switches that dictate a strict ceiling on our physical size. Once we reach sexual maturity, our skeletal structures fuse, our growth hormones shift focus, and we completely stop increasing in size. From that point forward, our energy is directed solely toward maintaining our existing structure and reproducing. Many deep-sea giants, particularly invertebrates like crustaceans, echinoderms, and mollusks, alongside certain primitive fish, are entirely free from this genetic ceiling. They possess the gift of indeterminate growth, meaning they never truly stop growing until the day they die. As long as they can successfully acquire nutrients and maintain their cellular stability, their biological programming instructs their bodies to keep expanding layer by layer, millimeter by millimeter, across their entire lives. Now, consider the mathematical intersection of indeterminate growth and an incredibly long lifespan. If an organism never stops growing, and its environment allows it to survive for hundreds of years without aging or suffering environmental catastrophe, the inevitable physical result is gigantism. A deep-sea creature does not necessarily need to grow rapidly to become a giant. It simply needs to survive. While a shallow water crab might grow quickly but die after 5 years due to predation or metabolic exhaustion, a deep-sea crab can grow at a microscopic rate of just a few millimeters a year. If that deep-sea crab remains undisturbed in the quiet abyss for 2 centuries, those tiny annual increments compound over time, ultimately producing a massive heavy-armoured titan with a spider-like frame. A spectacular real-world validation of this slow-motion, century-spanning growth model can be found in the deep benthic waters of the North Atlantic and Arctic Oceans, home to the Greenland shark. This creature lives at depths of up to 2,200 meters, in waters that are consistently near freezing. For generations, scientists were baffled by the immense size of these sharks, which can reach lengths of over 5 meters, despite having an incredibly sluggish movement speed and an almost undetectable metabolic rate. The breakthrough came when researchers utilized radiocarbon dating on the crystalline proteins inside the eyes of these sharks. Because these eye proteins are formed during embryonic development and never degrade or turn over during the animal's life, they serve as a perfect chemical time capsule. The results shocked the scientific community. The study revealed that the Greenland shark does not even reach sexual maturity until it is roughly 150 years old. The largest individuals examined were estimated to be between 300 and 500 years old, making them the longest-lived vertebrates known to science. The Greenland shark grows at an agonizingly slow rate of about 1 centimeter per year. It is a living testament to the fact that deep-sea gigantism is a product of deep time. Its massive 5-meter body is not the result of a rapid explosion of flesh, but rather a slow, steady accumulation of mass across centuries of quiet, uninterrupted existence in the cold dark. It was alive when Galileo pointed his first telescope at the stars, and it continues to swim through the dark today, still growing, still expanding. This absence of environmental disruption also extends to the realm of predation. In shallow waters, the density of hungry, highly active predators is immense. An animal must spend a vast amount of its energy fleeing, hiding, or defending itself. The risk of violent death is a constant factor that prevents most individuals from ever reaching their maximum theoretical lifespan. In the deep abyss, the density of life is incredibly low. While predators do exist, they are few and far between, and they operate under the same slow-motion, energy-saving rules as everyone else. The threat of immediate violent death is significantly reduced. This drop in predation pressure creates a safe haven where individuals can cross the centuries-long threshold required to maximize their indeterminate growth potential. Thus, the profound stability of the deep sea alters the very strategy of evolution. In a volatile world, nature favors species that live fast, reproduce in massive numbers, and die young, ensuring the survival of the gene pool through sheer volume. In the immutable silence of the abyss, nature selects for the opposite: extreme durability, meticulous cellular maintenance, and a slow, steady accumulation of mass over centuries. Gigantism in the deep sea is the physical manifestation of accumulated time. It is a visual monument to a world where the destructive fires of aging have been cooled by the abyssal ice, and where the frantic hurry of life has been replaced by a slow, majestic continuum. These deep-sea titans are not merely large animals. They're ancient biological fortresses that have stood the test of centuries, growing larger and more imposing with every passing year, completely detached from the brief, hurried lifespans of the world above. To bridge the gap between abstract physical laws and concrete biological reality, we must now conduct a rigorous examination of the specific animal lineages that have undergone this monumental transformation. We begin our survey with the most successful phylum in the history of animal life on Earth, the arthropods. On land, arthropods, including insects, arachnids, and land crustaceans, are strictly limited in size by their unique anatomical architecture. Because they possess rigid external skeletons made of chitin and rely on simple respiratory systems, a terrestrial arthropod that grows too large faces imminent death. Its heavy armour becomes too thick to move, and its inner organs suffocate under the weight of its own body. But when this exact same skeletal blueprint descends into the deep ocean, the rules change entirely. In the crushing dark, freed from gravity and supported by unique fluid dynamics, marine arthropods achieve sizes that border on the monstrous. Let us first analyse one of the most iconic symbols of deep-sea gigantism, the giant isopod, known scientifically as Bathynomus giganteus. To understand the scale of this creature, one must look at its terrestrial relatives. If you walk into a damp garden or lift a rotting piece of wood, you will likely find a common woodlouse or pillbug. These tiny, segmented terrestrial isopods rarely exceed a single centimetre in length. They are delicate scavengers that scramble away into the soil at the slightest disturbance. Now, follow this exact same creature down past the continental shelf into the cold, dark, benthic zone of the Atlantic and Pacific Oceans, thousands of metres beneath the surface. In this dark world, the tiny woodlouse is replaced by a heavy armoured titan. The giant isopod can grow to a length of over 40 centimetres and weigh nearly 2 kilograms. Seeing a giant isopod for the first time is a shocking experience. It looks like a prehistoric monster or a terrestrial pillbug that has been magnified dozens of times by a science fiction laboratory. Yet its anatomical blueprint remains remarkably similar to its tiny land-dwelling cousins. It possesses a heavily segmented exoskeleton, 14 specialised compound legs, and 2 large reflective eyes that gleam with an eerie pale light in the darkness of the abyss. How does the giant isopod sustain this massive chitinous frame in an environment characterised by extreme starvation? The answer lies in a highly specialised set of physiological and behavioural adaptations designed to maximise its metabolic efficiency. The giant isopod is primarily a benthic scavenger. It crawls slowly across the muddy floor of the abyssal plain, using its highly sensitive antennae to detect the faint chemical signatures of decaying organic material carried by the deep ocean currents. Because meals are exceptionally rare, the giant isopod has evolved a stomach that doubles as an elastic storage chamber. When it encounters a food source, such as a dead fish or a sunken shark carcass, it does not eat with moderation. It gorges itself with terrifying intensity, packing away chunks of flesh until its body becomes visibly bloated and its segmented plates stretched to their absolute limits. Once this feeding frenzy is complete, the giant isopod returns to a state of absolute kinetic silence. It settles onto the mud, folding its appendages beneath its heavy carapace, and enters a form of metabolic dormancy. Because the water temperature is near freezing, its internal chemical clock ticks at a microscopic speed. The massive volume of nutrients stored within its highly expanded digestive tract is processed with ultimate frugality. In a spectacular display of evolutionary endurance, captive giant isopods kept in public aquariums have been documented to survive for up to 5 consecutive years without consuming a single piece of food. This unbelievable feat of fasting is completely impossible for any small crustacean, proving that its giant size is not a biological hindrance, but rather a massive energy-saving fortress that insulates the animal against the constant threat of starvation. While the giant isopod represents a massive expansion of body volume and weight, we must turn our attention to another deep-sea arthropod that demonstrates gigantism through jaw-dropping skeletal extension, the Japanese spider crab, or Macrochaira kempferi. Inhabiting the deep benthic slopes of the Pacific Ocean surrounding Japan, particularly at depths ranging from 300 to 600 meters, this creature holds the undisputed title of the largest living arthropod on our planet. While its central body carapace is relatively modest, reaching a width of about 40 centimeters, its true scale is revealed when you look at its magnificent spindly appendages. From the tip of one massive claw to the tip of the opposite leg, a fully grown Japanese spider crab can achieve a terrifying silsa-like splay of nearly 4 meters. To survive at these depths with such a radically extended skeletal frame, the Japanese spider crab must overcome severe structural and mechanical challenges. On land, a creature with 4-meter legs made of rigid chitin would instantly collapse under the weight of gravity. The legs would snap like dry twigs, and the muscles required to lift those limbs would be too heavy to operate. In the deep sea, the natural buoyancy of water completely eliminates the downward pull of gravity. The crab is effectively weightless within its fluid environment. This allows evolution to completely abandon the heavy, thick structural reinforcements required for land animals, and instead focus on maximizing reach and leverage. The movement of the Japanese spider crab across the deep sea floor is a marvel of biological engineering. Its long, slender legs are jointed with extreme precision, allowing it to move with a slow, deliberate and ghostly grace that resembles a massive underwater spider moving in slow motion. Because the water at these depths is cold and highly viscous, moving rapidly would require an immense expenditure of precious calories. Therefore, the crab does not run or scurry. Instead, it utilizes its immense leg span to take massive, slow steps across the deep mud, covering substantial physical distances with a minimal number of muscular contractions. Each step spans a distance that a smaller crab would have to scurry for minutes to achieve. This long-striding mechanism allows the Japanese spider crab to patrol a vast home range on the deep ocean floor, maximizing its chances of finding food, while burning a fraction of the energy consumed by smaller short-legged crustaceans. Furthermore, the mechanical design of its long claws, known as chelipeds, is perfectly adapted to its lifestyle as both a slow scavenger and an opportunistic predator. In the male crabs, these claws grow significantly longer than the rest of their legs, providing an incredible mechanical advantage. They can reach into deep rocky crevices, pull apart decaying carcasses, or crush the shells of slow-moving mollusks and echinoderms with minimal bodily movement. The crab can remain perfectly still, conserving its metabolic energy, while its long crane-like limbs do all the work of searching and gathering food across a wide radius. We must also examine the unique challenges that these giant arthropods face regarding the process of molting, or ecdysis. Because an arthropod skeleton is on the outside of its body, it cannot grow continuously in the way a human or a fish does. To increase its physical size, a crustacean must periodically shed its entire existing exoskeleton, expand its soft inner tissues by absorbing water, and then wait for a new, larger shell to harden. For a shallow water crab or shrimp, molting is a highly frequent and dangerous process that occurs dozens of times throughout its brief lifespan. For a giant deep-sea arthropod, the physics of molting becomes an existential crisis. Shedding a 4-meter exoskeleton or a massive heavy isopod shell requires an immense amount of metabolic energy, a resource that is incredibly scarce in the abyss. Furthermore, once the old shell is discarded, the animal's body is completely soft and defenseless, leaves it highly vulnerable to any predators and to the immense mechanical stress of the surrounding environment. To adapt to this crisis, deep-sea giants have radically altered their molting schedules. They grow at an exceptionally slow rate, meaning they only molt once every several years or even decades. As they reach their advanced giant stages, many of these creatures undergo a final terminal molt, after which they never shed their shell again. Their genetic programming instructs them to stop shedding, and instead focus all of their resources on maintaining the thick calcified chitin they already possess. Over the centuries, this permanent armour becomes encrusted with deep-sea bryozoans, barnacles, and marine worms, transforming the elderly giant into a walking living reef. This total cessation of frequent molting saves vast amounts of metabolic energy, allowing the animal to redirect its limited caloric intake towards sustaining its massive internal organs and ensuring long-term survival in the food-starved wilderness. Thus, when we analyse the deep-sea arthropods, we see that gigantism is a masterstroke of structural adaptation. By utilising the natural buoyancy of the dense, cold ocean water, these creatures have shattered the physical size limitations that keep land insects and spiders tiny. The giant isopod uses its expanded volume to form an ultra-efficient storage fortress against famine, capable of waiting years between meals. The Japanese spider crab uses its spectacular leg span to glide effortlessly over the high-viscosity water, turning a barren sea floor into an easily navigable territory. They are true marvels of mechanical and physiological design, living proof that when the constraints of gravity and rapid metabolism are stripped away, the humblest blueprints of life can expand into awe-inspiring titans of the deep. While the armoured arthropods rule the muddy plains of the ocean floor, another lineage of ancient animals dominates the vast, dark water column of the pelagic abyss. These are the cephalopods, the most neurologically advanced and physically dynamic invertebrates on Earth. In shallow coastal waters, octopuses, cuttlefish, and squids are known for their intelligence, rapid camouflage, and highly active predatory lifestyles. However, because they possess soft, unprotected bodies and operate with rapid metabolisms, their sizes are generally constrained to a manageable scale. But as we drop down past the twilight zone and enter the vast bathypelagic realm, the soft-bodied blueprint of the cephalopod undergoes a breathtaking evolutionary expansion. Here, in the open, ink-black water, we encounter the true phantoms of the deep sea, the giant squid, known scientifically as Architeuthis dux, and its even more massive southern relative, the colossal squid, or Mesonicoteuthis hamiltoni. To appreciate the sheer scale of these abyssal hunters, we must analyse their radical anatomical architecture. The giant squid is a creature of linear majesty. A fully matured individual can reach an astonishing length of up to 13 metres from the tip of its tail fin to the very ends of its primary feeding tentacles. Much of this length is comprised of its two specialised feeding tentacles, which can be shot forward like long muscular ropes to snare prey from a distance. The central mass of the body, the mantle, which houses the vital organs, can still reach lengths of over 2 metres. Its close relative, the colossal squid, which inhabits the freezing waters surrounding Antarctica, takes a different structural approach. Rather than relying on long, slender tentacles, the colossal squid evolves a shorter, immensely thick and heavy mantle, making it the heaviest invertebrate known to science, with weights exceeding 500 kilograms. Living in an environment of total darkness, these massive cephalopods have had to completely redesign their sensory apparatus, leading to the development of the most spectacular visual organs in the animal kingdom. The eyes of the giant squid and colossal squid are truly monstrous, reaching diameters of up to 27 centimetres, roughly the size of a standard regulation basketball. No other animal on Earth, including the largest blue whales, possesses eyes of this magnitude. From an evolutionary standpoint, building an eye of this size requires an immense investment of metabolic energy and physical space. Why did the laws of deep-sea survival mandate such a radical optical investment? The answer is tied to the unique physics of light transmission in deep water. Beyond a depth of 1,000 metres, absolutely zero sunlight penetrates the ocean. the environment is dark, save for one crucial element: bioluminescence. Nearly 90% of deep-sea organisms possess the chemical ability to produce their own light, creating a sparse, flickering tapestry of glowing flashes, sparkles, and chemical clouds in the dark water. A standard-sized eye, like those found in shallow water fish, is completely incapable of capturing these faint, isolated photons across long distances. By scaling their eyes up to the size of basketballs, giant squids maximize the surface area of their pupils and lenses, allowing them to gather an immense volume of ambient light. This structural magnification provides them with an incredibly high contrast sensitivity. However, mathematical models indicate that these giant eyes are not designed to hunt tiny, glowing shrimp or small fish in the dark. Instead, they are specifically tuned to detect the movement of massive objects. The primary driver behind the evolution of the giant squid's immense eye is its relationship with its ultimate predator, the sperm whale. The sperm whale is a massive air-breathing mammal that regularly dives to depths of over 2,000 meters to hunt these giant cephalopods. As the sperm whale swims through the deep ocean water, its massive body inevitably collides with dense swarms of microscopic bioluminescent plankton and small jellyfish. This collision causes the tiny organisms to flash with defensive light, creating a massive glowing silhouette or wake that follows the whale through the dark. A giant squid, sitting quietly in the absolute darkness, can use its basketball-sized eyes to detect this glowing wake from a distance of over 100 meters away. This crucial visual warning gives the squid a temporary tactical advantage, allowing it to initiate evasive maneuvers or slip silently into the dark water column long before the whale can pinpoint its exact location with echolocation. The giant eye is an early warning missile defense system, engineered to survive a relentless evolutionary arms race in the dark. When we look beyond their eyes at their predatory apparatus, we see that these giant cephalopods are built for highly efficient ambush-style hunting. In the shallow waters, squids use jet propulsion to dart around at high speeds, a lifestyle that burns a massive amount of energy. In the food-starved abyss, a giant squid cannot afford to constantly jet through the water column. It would burn through its energy reserves within hours and starve. Therefore, the muscular composition of the giant squid's mantle is highly specialized. Unlike the firm, muscular flesh of shallow water squids, the tissue of the giant squid contains a very high concentration of ammonium ions. Ammonium is less dense than seawater, providing the giant squid with neutral buoyancy. The creature does not need to expend a single calorie to maintain its position in the water column. It simply hovers effortlessly like a ghostly, silent blimp. Its massive fins are used for gentle, precise steering rather than high-speed propulsion. This neutral buoyancy allows the giant squid to conserve its precious metabolic energy, remaining completely stationary for hours until an unfortunate fish or a smaller squid swims within range. When prey does arrive, the attack is swift and devastating. The giant squid launches its two long feeding tentacles, which are armed with powerful circular suckers ringed with sharp, serrated teeth made of chitin. The prey is instantly snared and dragged toward the center of the squid's 8 arms. Here, the true power of the cephalopod anatomy is revealed. The squid possesses a massive heavy beak made of cross-linked proteins and chitin, which looks remarkably like the beak of a giant parrot. This beak is operated by massive, powerful muscles capable of slicing through thick fish scales, dense muscle tissue, and solid bone with absolute ease. Inside the beak lies the radulae, a spiked ribbon-like tongue that acts as a meat grinder, shredding the food into tiny pieces before it passes through the brain and down into the stomach. This precise fragmentation is anatomically non-negotiable for the giant squid, because its unique ring-shaped brain actually wraps directly around its esophagus. If the squid attempted to swallow a large, unchewed chunk of food, it would literally suffer catastrophic brain damage. The ecological role of these giant cephalopods within the deep-sea food web is complex, and represents a massive vertical connection between the surface world and the deep abyss. For centuries, the giant squid was viewed as a legendary sea monster, the kraken, capable of dragging entire ships beneath the waves. But scientific reality paints a far more fascinating picture of an animal that forms the cornerstone of a massive deep-water ecosystem. While they are formidable apex predators to the smaller fish and squids of the bathypelagic zone, they are simultaneously the primary food source for the largest mammalian predators on Earth. The scale of this predator-prey relationship is staggering. When scientists examine the stomach contents of stranded sperm whales, they routinely find thousands of undigested chitinous squid beaks. In fact, statistical analysis of these stomach samples suggests that sperm whales consume millions of giant and colossal squids globally every single year. This indicates that these giant cephalopods are not rare, isolated freaks of nature. They exist in massive numbers throughout the global ocean, forming a highly successful hidden population that thrives in the vast mid-water wilderness. The battles between these two titans are etched directly onto the skin of the whales themselves. Because sperm whales possess thick, blubbery skin, they carry permanent scars from their encounters in the dark. Many adult sperm whales are covered in massive circular white scars caused by the serrated suckers of giant squids fighting for their lives as they are dragged toward the whale's toothy lower jaw. In some cases, these circular scars measure up to 10 centimeters in diameter, hinting at the immense physical struggles that take place miles beneath the waves, completely hidden from human sight. In the case of the colossal squid, the stakes are even higher. The suckers of the colossal squid do not merely feature tiny chitinous teeth. They have evolved into free-rotating, razor-sharp, swiveling hooks that can measure several centimeters in length. These hooks can slice deep gashes into the flesh of a hunting sperm whale, forcing the mammal to expend massive amounts of energy to secure its meal. Thus, when we analyze the cephalopods of the deep sea, we see a completely different manifestation of gigantism compared to the benthic arthropods. While the crabs and isopods grow large to withstand the physical pressures of the mud and store food for years, the giant and colossal squids use their immense scale to conquer the open water column. They utilize chemical adaptations like ammonium ions to achieve perfect neutral buoyancy, transforming themselves into energy-efficient stealth platforms. They build basketball-sized eyes to decipher the complex language of bioluminescence and detect the arrival of giant predators in a world with zero sunlight. They are the undisputed rulers of the mid-water abyss, majestic, intelligent, and perfectly engineered titans that prove that even the softest, most vulnerable blueprints of life can expand into magnificent apex predators when shaped by the unique demands of the deep ocean. Transitioning from the soft-bodied marvels of the open water column, we must now direct our scientific focus toward the most dominant and diverse group of vertebrates in the global ocean, the fish. In the sunlit layers of the sea, bony and cartilaginous fishes have evolved into thousands of highly specialized forms, optimized for rapid acceleration, tight schooling maneuvers, and aggressive territorial defense. However, these surface lifestyles require a high, continuous intake of calories and complex skeletal structures capable of withstanding the chaotic currents of coastal ecosystems. As these vertebrate lineages descend into the deep bathypelagic and benthic zones, their anatomical frameworks are radically overhauled by the forces of evolution. In this section, we will analyze how the vertebrate blueprint adapts to the absolute stillness and scarcity of the deep sea, focusing on two extraordinary examples: the long bony marvel known as the oarfish and the ancient cartilaginous predators represented by deep-sea sharks. Let us first examine the longest bony fish alive on Earth today, the giant oarfish, classified scientifically as Regalicus gleston. For centuries, this enigmatic creature was responsible for terrifying sailors and spawning global legends of monstrous sea serpents undulating at the surface of the water. When an oarfish occasionally washes ashore or is spotted dying near a coastal beach, its appearance is profoundly alien. It possesses a radically elongated, ribbon-like body that can reach verified lengths of up to 8 meters, with some unverified scientific estimates pushing closer to 11 or 12 meters. Despite this incredible length, its body is remarkably narrow, often measuring only a few centimeters in width, and its skin lacks traditional scales. Instead, its silver flanks are covered in a rough tubercular layer of a compound known as guanine, which reflects the faintest traces of light like a mirrored blade. To understand why the oarfish adopts such an extreme, elongated physical structure, we must analyze its unique locomotion and ecological position within the deep sea. The oarfish primarily inhabits the mesopelagic and bathypelagic zones, down to depths of roughly 1,000 meters. In this calm, current-free environment, the energetic cost of swimming horizontally like a standard trout or tuna would be completely unsustainable. Therefore, the oarfish does not swim horizontally. Instead, it spends much of its life suspended in a completely vertical position, with its head pointing directly upward toward the distant surface and its long ribbon-like body trailing straight down into the abyss. This vertical posture is maintained with absolute energetic efficiency through a specialized form of locomotion known as amyoform swimming. The oarfish possesses a brilliant crimson dorsal fin that runs uninterrupted along the entire length of its multi-meter body. To hover in place or move gently through the water column, it does not flex its massive body muscles, which would burn immense amounts of glycogen and oxygen. Instead, it passes continuous, gentle waves of muscular contraction solely through its long dorsal fin. This undulating fin behaves like a highly precise low-energy underwater thruster, allowing the oarfish to hang silently in the dark water column like a silver ribbon, completely invisible to both its predators and its prey. This vertical lifestyle is directly linked to its feeding mechanism. Despite its monstrous sea serpent appearance, the giant oarfish is a gentle filter feeder. It positions itself vertically directly beneath dense swarms of tiny bioluminescent krill, small crustaceans, and miniature jellyfish. Because its eyes are positioned to look forward and upward, its vertical orientation allows it to silhouette its tiny prey against any faint bioluminescent glow or downwelling light. When it detects a cluster of food, it utilizes a highly specialized, highly expandable mouth to rapidly create a vacuum, pulling the water and the crustaceans inside. The prey is then trapped by a dense network of long, rigid structures inside its gills known as gill rakers. By growing to a length of 8 meters while maintaining an ultra-thin, low-mass profile, the oarfish maximizes its vertical reaching capacity and its sensory coverage of the water column, while minimizing the total volume of living tissue it must energetically maintain through metabolism. Furthermore, the oarfish exhibits a highly unusual biological phenomenon known as autotomy, which directly assists in its long-term survival under starvation conditions. When marine biologists examine fully grown oarfish specimens, they frequently discover that the terminal tail portion of the fish has been cleanly severed and healed over. The oarfish is capable of deliberately shedding the lower sections of its long body when it suffers from severe food shortages or when it is attacked by deep-sea predators like large squids or sharks. Because its vital organs are all compressed into the extreme anterior portion of its body, right behind its head, the remaining meters of its tail are essentially non-vital structural tissue. By sacrificing its tail, the oarfish reduces its total body mass, lowers its baseline metabolic requirements, and escapes immediate death, allowing it to continue surviving in the nutrient-poor wilderness of the deep water column. While the oarfish represents the extreme extension of the bony fish framework, we must descend even further down to the very floor of the deep ocean to analyze the ancient lords of cartilaginous biology, deep-sea sharks. Unlike bony fishes, sharks do not possess hard, calcified skeletons. Their structural framework is composed entirely of flexible, lightweight cartilage. On land or in shallow water, cartilage is often considered less structurally supportive than bone, but in the deep sea, this flexible material provides a massive evolutionary advantage. As we analysed in previous sections, at extreme depths and low temperatures, calcium carbonate becomes highly soluble and begins to dissolve, making the maintenance of a heavy bony skeleton an energetic nightmare. Cartilage, by contrast, requires no calcium investment and is completely unaffected by the chemical dissolving power of the abyss. One of the most profound examples of ancient shark gigantism is the blunt-nosed six-gill shark, known scientifically as Hexantius gracieus. This massive predator can be found at depths extending past 2,000 metres, patrolling the cold benthic slopes of the global ocean. While most modern surface sharks have evolved highly efficient, five-gilled respiratory systems optimised for rapid, high-oxygen swimming speeds, the blunt-nosed six-gill shark retains an ancient primitive anatomy featuring 6 distinct gill slits. It can reach lengths of over 5 metres and weigh more than 600 kilograms, matching the physical dimensions of the famous great white shark of the surface world. How does a predatory shark maintain such a massive physical presence in an ecosystem where prey animals are few and far between? The secret lies in a profound anatomical transformation of its liver and muscle tissue. In shallow water sharks, the liver is an important organ for buoyancy, filled with low-density oils like squalene. In deep-sea giants like the six-gill shark, this organ undergoes a massive expansion, sometimes accounting for up to 25% of the animal's entire body weight. This colossal liver is saturated with lightweight lipids that perfectly counterbalance the weight of its muscles and cartilage, granting the 5-metre shark absolute, perfect, neutral buoyancy in the dense, near-freezing water. Because it is perfectly counterbalanced, the six-gill shark does not need to swim forward continuously to prevent itself from sinking, unlike its surface-dwelling relatives. It can glide over the ocean floor with the absolute minimum of muscular effort. Its muscle fibres are completely different from those of fast-surface predators. They're composed almost entirely of white muscle fibres designed for slow, sustainable, low-oxygen cruising with very little dark, high-oxygen muscle. The flesh of a deep-sea shark is soft, watery and loose, filled with high concentrations of compounds like urea and trimethylamine oxide to stabilize its cellular proteins against the immense hydrostatic pressure. This slow-motion cruising mechanism is an elite strategy for long-distance scavenging. The blunt-nosed six-gill shark operates primarily as an opportunistic apex scavenger. It uses its highly developed olfactory organs to detect the faint chemical trails of decaying fats and proteins drifting from a distance of several miles away. When it locates a massive food event such as a whale fall, its massive size becomes its ultimate asset. Armed with multiple rows of specialized saw-like teeth on its lower jaw and sharp, gripping teeth on its upper jaw, it can carve massive, high-calorie chunks of blubber and flesh from the carcass, packing its highly distensible stomach to maximum capacity. We must also acknowledge the Greenland shark, which we previously discussed in the context of extreme longevity, as another prime model of this deep, cartilaginous gigantism. Living in the absolute freezing waters of the deep Arctic, its metabolism is so incredibly slow that its maximum swimming speed is less than 3 kilometers per hour. Yet, it reaches lengths of over 5 meters. Because it cannot chase down active prey, it has evolved into the ultimate slow-motion stealth hunter. It utilizes a highly specialized form of crypsis, aided by bioluminescent ocular parasites that attract curious fish directly toward its mouth in the dark. It glides through the black water column like an inanimate frozen log, expending almost 0 calories until an unwary seal or large fish swims directly into its path. Thus, when we analyze the fish lineages of the deep sea, we see 2 completely divergent architectural solutions to the exact same environmental challenges. The giant oarfish utilizes structural elongation and vertical suspension, converting its multi-meter frame into a highly efficient low-energy filter feeding blade that hovers silently through the use of a single undulating fin. The deep-sea sharks, such as the blunt-nosed six-gill and the ancient Greenland shark, exploit the natural advantages of a non-calcified cartilaginous skeleton, combined with massive lipid-rich livers to achieve flawless neutral buoyancy. They discard the heavy, energetic demands of rapid muscular movement, choosing instead to become massive slow-motion cruising platforms capable of tracking food across vast underwater deserts. These vertebrate titans prove that when the biological need for high-speed competition is eliminated by the cold and the dark, life can slow its pace down to a majestic crawl, allowing animals to expand their physical frameworks across vast dimensions of space and time. While the vast plains of the abyssal mud and the open spaces of the water column are defined by extreme food scarcity, there are specific zones on the ocean floor where energy is not scarce, but incredibly concentrated. These are the hydrothermal vent fields and cold seeps, regions where tectonic plates tear apart and allow superheated, mineral-rich water to spew directly into the near-freezing ocean. In these bizarre underwater volcanic oases, life breaks entirely away from the traditional solar economy. There is zero sunlight, meaning traditional photosynthesis is completely impossible. Instead, the entire ecosystem is powered by chemosynthesis, the chemical conversion of toxic compounds into organic energy. In this section, we will analyse how invertebrates have evolved to harness this dark chemical power, focusing on the incredible biological mechanics of the giant tube worm, known as Riftia pachyptila, and the massive pelagic cnidarians represented by the giant deep-sea jellyfish. Let us first explore the absolute marvel of chemosynthetic engineering, the giant tube worm. Discovered in the late 20th century along the Galapagos Rift and the East Pacific Rise at depths of over 2,500 metres, these creatures completely revolutionised our understanding of biological possibilities. Growing up to lengths of over 2 metres, these worms live packed together in dense, towering colonies that surround the mineral chimneys of hydrothermal vents. They reside inside rigid protective tubes made of a tough mixture of chitin and protein, which they cement directly to the volcanic rocks. From the tops of these white tubes they extend brilliant blood-red plumes into the water, creating a stark visual contrast against the dark, rocky seafloor. To understand how a worm can grow to a length of 2 metres in an environment without sunlight, we must analyse its radical internal anatomy. The giant tube worm is completely devoid of a traditional digestive tract. It possesses no mouth, no gut, no anus, and no stomach. It cannot chew, swallow, or digest food in any conventional sense. From an evolutionary perspective, this seems like a fatal anatomical design. Yet the worm grows faster than almost any other marine invertebrate on Earth, expanding its body mass at an astonishing rate. The secret to this rapid, sunless growth lies in an extraordinary symbiotic relationship with specialised bacteria. Inside the body cavity of the giant tube worm lies a massive, highly vascularised organ known as the trophosome, which accounts for a substantial percentage of the worm's total body weight. This trophosome is literally packed with billions of sulfur-oxidizing bacteria. The worm and the bacteria operate as a single, highly integrated metabolic unit. The process begins at the bright red plume of the worm. This plume is flooded with a highly specialized form of hemoglobin, the iron-bearing protein that binds gases. Unlike human hemoglobin, which only carries oxygen, the hemoglobin of the giant tube worm has evolved the unique chemical capability to simultaneously bind oxygen and hydrogen sulfide, a highly toxic compound that smells like rotten eggs and would instantly kill almost any other animal on Earth by shutting down cellular respiration. The superheated fluid spewing from the hydrothermal vents is saturated with this toxic hydrogen sulfide. The worm's plume absorbs both the oxygen from the cold deep water and the hydrogen sulfide from the volcanic vent fluid. The specialized hemoglobin locks these volatile gases into the bloodstream, preventing the toxic sulfide from poisoning the worm's own tissues, and transports them down into the trophosome. Once inside, the symbiotic bacteria take over. They absorb the hydrogen sulfide and use oxygen to chemically oxidize it, stripping electrons from the sulfur molecules. The bacteria harvest the chemical energy released by this oxidation process and use it to drive the Calvin cycle, converting dissolved inorganic carbon dioxide into complex organic molecules like sugars, amino acids, and lipids. The bacteria then leak these freshly synthesized organic compounds directly into the bloodstream of the giant tube worm, providing it with an endless, highly concentrated supply of pure nutrients. In return, the worm provides the bacteria with a safe, stable home and a continuous high-speed delivery pipeline of raw materials. Because this chemical energy loop operates independently of the slow, seasonal drift of marine snow from the surface, the giant tube worm is freed from the starvation constraints that limit other deep-sea animals. It has tapped into a direct volcanic power grid, allowing its cells to divide and expand with immense speed, building 2-meter structures without ever needing a single ray of sunlight. While the giant tube worm represents a sedentary, benthic mastery of chemosynthetic ecosystems, we must move back into the water column to analyse a completely different type of sunless giant that rules the pelagic abyss: the giant deep-sea jellyfish, specifically Stygiomedusa gigantea, often referred to as the giant phantom jelly. Inhabiting the bathypelagic zone at depths ranging from 1,000 to 4,000 metres, this enigmatic cnidarian is one of the largest invertebrate predators in the open ocean. It features a massive, thick umbrella-shaped bell that can measure over 1 metre in diameter, from which extend 4 enormous, thick, curtain-like oral arms that can reach lengths of up to 10 metres. To appreciate the gigantism of Stygiomedusa gigantea, we must contrast it with the jellyfish of the surface world. Shallow water jellyfish rely on dozens of thin, hair-like tentacles lined with stinging cells, known as nematocysts, to capture tiny drifting plankton or small fish. They are translucent, delicate, and highly dependent on the dense concentrations of life found in sunlit waters. Stygiomedusa, by contrast, has completely abandoned thin, stinging tentacles. Instead, its body is composed of a deep, dark, reddish-purple or velvety black gelatinous tissue that absorbs any traces of bioluminescent light, making it completely invisible in the dark water column. The evolutionary path to gigantism in this deep-sea jellyfish is driven by a unique optimization of fluid dynamics and tissue composition. Jellyfish are composed almost entirely of water, often exceeding 95% of their total mass. This means that building a 10-meter structure requires very little actual organic carbon or metabolic energy compared to building a 10-meter fish or whale. In the cold, dense, and highly viscous water of the deep sea, a massive soft gelatinous body becomes an exceptionally efficient mechanical tool. Stygiomedusa gigantea does not actively swim through the water column to chase down prey. Doing so would burn through its limited energy reserves. Instead, it utilizes its massive 1-meter bell to perform slow, rhythmic, low-frequency contractions, creating gentle pressure waves that propel it through the abyss. As it moves with ghostly slowness, its 4 10-meter oral arms trail behind it, like massive, flexible velvet curtains. These arms are not designed to sting tiny shrimp. Instead, they function as a massive moving trap designed to envelop larger, slow-moving deep-sea organisms, such as deep-sea fish, smaller jellies, and detrital aggregates. The relationship between these pelagic giants and the sunless economy is tied to their role as massive nutrient concentrators. Because Stygiomedusa operates with an incredibly low metabolic rate, it can maintain its vast 10-meter frame on a surprisingly small number of sporadic high-calorie captures. When it does capture food, its vast oral arms guide the prey into its central gastrovascular cavity, where it is slowly broken down over days. The sheer surface area of its 10-meter arms allows it to sweep through a massive volume of water with every slow stroke, turning the vast emptiness of the bathypelagic zone into a highly effective harvesting field. Furthermore, These giant jellyfish often form localized microecosystems in the open water. Small deep sea fishes, such as the pelagic whiting, have been observed living in a symbiotic relationship inside the bell and among the massive oral arms of Stygiomedusa. The giant jellyfish provides these small fish with a moving fortress that protects them from larger predators in the open water, while the fish potentially assist the jelly by picking away parasites or consuming scraps of food that escape the jelly's primary digestive centre. Thus, when we survey the invertebrates that thrive without sunlight, we see two brilliant demonstrations of evolutionary expansion. The giant tube worm, Riftia percipitella, achieves gigantism by forming a flawless chemical alliance with sulfur-oxidizing bacteria, bypassing the solar food chain entirely to convert toxic volcanic chemicals into explosive physical growth. The giant phantom jelly, Stygiomedusa gigantea, exploits the mechanical properties of highly hydrated, low-density gelatinous tissue to construct a massive 10-meter predatory web that sweeps through the dark water column with absolute energetic efficiency. These creatures are living proof that life does not require the sun to achieve greatness. In the darkness of the abyss, whether fueled by the volcanic heat of the Earth's core or the clever optimization of gelatinous mass, nature finds a way to tear down traditional biological limits, engineering magnificent titans that rule a world of perpetual night. To synthesize our understanding of the monstrous scaling that occurs within the ocean depths, we must look beyond individual environmental parameters and piece together the comprehensive evolutionary canvas of the abyss. Gigantism is not merely a reactionary shield against cold water or high osmotic pressures, it is an optimized macro-evolutionary trajectory. When a taxonomic lineage descends into the deep ocean over millions of years, its entire genetic architecture is subjected to a profound restructuring. This evolutionary landscape operates under a completely unique set of selective pressures compared to the surface world. Two of the most critical factors driving this systemic change are the radical shift in predator-prey dynamics, specifically the near-complete absence of highly active, warm-blooded apex predators, and the molecular modifications occurring within the genomic sequences that dictate cellular growth and structural limits. Let us first dismantle the ecological theatre of the deep sea by looking at predation pressure. In the shallow zones of the global ocean, life is defined by a relentless, high-speed game of survival. Coral reefs, mangrove swamps, and sunlit pelagic waters are densely packed with highly agile, intelligent, and fiercely competitive predators. Sharks, barracudas, tuna, billfish, and marine mammals like dolphins and killer whales maintain a constant high-stakes surveillance network over every cubic meter of water. In such a high-velocity environment, growing to an intermediate or massive size without possessing extreme speed or thick protective armour is an evolutionary death sentence. An animal that is large but slow becomes an unmissable high-calorie target for a pack of highly coordinated hunters. Therefore, shallow water evolution frequently prioritizes small sizes for concealment or aerodynamic agility for rapid flight. As we drop past the boundaries of the epipelagic zone and descend thousands of meters into the abyssal plain, this predatory matrix completely dissolves. The primary reason for this dissolution is energetic. Warm-blooded mammals and highly active, endothermic predatory fish require a continuous massive supply of calories to maintain their high body temperatures and furious metabolic demands. Because less than 1% of the ocean's primary organic productivity ever reaches the deep sea, the abyss simply cannot provide the caloric density required to support a resident population of fast-moving, high-energy apex predators. A pod of killer whales or a school of bluefin tuna would starve to death within weeks if they attempted to establish a permanent home on the abyssal floor. This absence of high-energy, warm-blooded hunters creates an unprecedented evolutionary sanctuary for cold-blooded invertebrates and primitive fishes. In the deep sea, the organisms that occupy predatory roles are themselves bound by the slow-motion, energy-conserving rules of the abyss. They are ambush predators that spend hours hovering in place, or slow-moving scavengers that cruise the mud with minimal muscular effort. The relentless, high-speed chase sequences that define surface predation are completely non-existent in this dark world. For a developing species, this reduction in active predation pressure completely alters the selective cost-benefit analysis of body size. In the absence of fast visual hunters that can easily spot and track a large silhouette, the traditional dangers of being large are completely neutralized. An organism can grow to massive proportions without the fear that its size will make it a vulnerable target. Furthermore, because there are no fast-moving competitors to outrun, the animal does not need to allocate its limited caloric resources toward building complex high-velocity locomotive muscles or maintaining rapid neurological reflexes. Every single calorie it captures can be directed toward a single, uninterrupted biological objective: the steady, long-term expansion of its structural mass. The abyss acts as an evolutionary greenhouse where, free from the pruning shears of active predators, the branches of life can stretch outward to maximum length. This lack of predation pressure interacts directly with the molecular machinery of life, bringing us to the second great evolutionary pillar of deep-sea gigantism, genomic modification. To understand how a species shifts its size across evolutionary time, we must look at the genetic blueprints that control growth, specifically the regulatory genes that dictate cell division, lifespan, and overall body proportions. Every living organism possesses a highly conserved set of genetic switches that act as biological brakes and accelerators for growth. In recent years, marine genomicists have begun sequencing the deoxyribonucleic acid of deep-sea titans, comparing their genetic codes to their tiny shallow-water relatives. The discoveries have been profound. In deep-sea giants, such as the giant isopod or various deep-sea echinoderms, scientists have identified major structural variations and mutations within the genes that regulate the insulin-like growth factor signaling pathway. This specific biochemical pathway is the universal master controller of body size and tissue growth across almost all animal life. In shallow water species, the insulin-like growth factor pathway is tightly regulated by a series of genetic feedback loops. When an animal reaches a specific developmental milestone, these genetic brakes are activated, shutting down the production of growth hormones and forcing the organism to channel its energy into reproduction. This genetic constraint ensures that the animal remains within an optimal size range that balances food requirements with predator evasion. In the genomes of deep-sea giants, these genetic brakes have been systematically altered, dampened, or completely turned off by millions of years of natural selection. Because the environment does not penalize large size, mutations that allow the growth pathway to remain permanently open are not weeded out by natural selection. Instead, they are actively rewarded. The genetic accelerators for growth are allowed to run continuously across the entire duration of the animal's life. The cells of these organisms retain a permanent youthful capacity for expansion and protein synthesis, leading directly to the phenomenon of indeterminate growth that we analysed previously. Furthermore, the genomic analysis of deep-sea titans reveals a fascinating expansion in the number of gene copies dedicated to cellular repair, antioxidant production, and genomic stability. For an organism to survive for centuries and continuously grow to a massive size, it must possess an elite internal defense system capable of preventing genetic mutations and cellular collapse. When scientists sequenced the genome of deep-sea macrofauna, they discovered that these creatures possess multiple, duplicated copies of genes responsible for detecting and repairing breaks in double-stranded deoxyribonucleic acid. They also exhibit an upregulation of genes that produce heat shock proteins and molecular chaperones, which ensure that cellular proteins maintain their correct three-dimensional shapes under the immense structural strain of hydrostatic pressure. This genetic reinforcement package allows the animal's tissues to expand safely over hundreds of years without developing the cellular cancers or structural degradations that typically limit the lifespans of large terrestrial animals. We must also analyse this evolutionary picture through the lens of island biogeography, a scientific theory pioneered by Robert MacArthur and Edward O. Wilson, which features a famous component known as the island rule or Foster's rule. This ecological principle states that when small animals colonize an isolated island, they tend to evolve into giant forms across generations due to the absence of large competitors and predators. Conversely, large animals that colonize an island tend to dwarf due to limited resources. The deep ocean abyss behaves from an evolutionary standpoint exactly like a massive, inverted global island. It is a highly isolated, distinct ecosystem separated from the rest of the biosphere by an immense barrier of pressure and darkness. When small, primitive invertebrates from the continental shelves slowly expanded downward into this dark world over evolutionary epochs, they found themselves on a vast, predator-free island. The ecological niches for large, dominant scavengers and apex predators were completely empty. Through the mechanism of adaptive radiation, the colonizing species began to expand their physical dimensions to fill these vacant ecological roles. A small crustacean that acted as a simple, minor scavenger in shallow water found that in the deep sea, by opening its genetic growth pathways and expanding its mass, it could become the dominant, undisputed lord of the benthic plain, capable of monopolizing massive food events like whale falls. The island rule operates on a monumental scale within the deep sea, pushing the small and the humble to claim the crown of gigantism in an uncrowded world. Finally, we must consider the immense role of evolutionary inertia. Once a species begins down the pathway of deep-sea gigantism and successfully restructures its metabolism, life history, and genome to support a massive, slow-moving frame, the process becomes self-reinforcing. A giant body creates a massive physiological buffer that protects the species against short-term environmental fluctuations. If a localized region of the deep sea experiences an extreme drought of marine snow or a complete absence of large carcasses for a decade, the smaller, shorter-lived species in that area may suffer localized extinction because their biological margins for error are too thin. The deep-sea giants, with their century-spanning lifespans, massive lipid storage reserves, and ultra-efficient metabolisms, can comfortably ride out these multi-year resource depressions. They act as the permanent anchor points of the deep-sea ecosystem, maintaining stable populations across vast stretches of time. Thus, when we step back to gaze at the complete evolutionary tapestry of the deep sea, we see that gigantism is the logical, inevitable conclusion of a perfectly balanced biological equation. It is the majestic result of an ecosystem that has stripped away the chaotic, high-speed violence of surface predation and replaced it with a grand, quiet sanctuary. Within this sanctuary, the traditional structural and temporal boundaries of life are dismantled. Bounded no longer by genetic ceiling switches or the fear of active hunters, the DNA of these deep-sea pioneers adapts with absolute freedom. They rewrite their growth pathways, expand their repair mechanisms, and utilize the physics of buoyancy to transform their bodies into living monuments of evolutionary endurance. The titans of the abyss are the ultimate proof that when nature removes the pressure of competition and grants the gift of infinite time, the simplest blueprints of life will always expand to touch the very limits of physical possibility. While the deep ocean abyss has functioned as a monumental fortress of stability for millions of years, protecting its giant inhabitants from the chaotic fluctuations of the surface world, this ancient sanctuary is now facing an unprecedented ecological crisis. The walls of the abyss are being breached by the far-reaching chemical and thermal signatures of human activity. For centuries, humanity viewed the deep ocean as an infinite, unalterable void, a world too vast and remote to ever be impacted by the actions of a land-dwelling species. But modern oceanography has shattered this illusion. The deep sea is intimately connected to the global atmosphere through the continuous circulation of oceanic currents. As we look toward the future, the unique evolutionary strategy of deep-sea gigantism, which once represented the ultimate triumph of biological endurance, is rapidly transforming into a fatal vulnerability. The primary drivers of this modern ecological threat are the accelerating warming of the deep water masses and the systemic decline in dissolved oxygen concentrations, a phenomenon known as ocean deoxygenation. To understand why future changes pose such an existential threat to deep-sea giants, we must first revisit the delicate biological equilibrium that made their existence possible in the first place. Throughout this documentary, we have established that deep-sea gigantism relies on a highly precise thermodynamic and chemical equation. Extreme cold combined with maximum oxygen saturation. The freezing temperatures slow down cellular metabolism, allowing cells to operate with ultimate efficiency and grow larger before dividing, while the high concentrations of dissolved oxygen carried down by polar currents remove the physical barriers to tissue thickness and body volume. If you alter either of these variables, the entire structural and physiological framework of deep-sea gigantism begins to collapse like a house of cards. Let us first analyse the terrifying physics and biology of ocean warming as it penetrates the deep sea. The global ocean acts as the primary thermal buffer for our planet, absorbing more than 90% of the excess heat trapped in the atmosphere by greenhouse gas emissions. For a long time, this heat absorption was primarily concentrated in the upper hundreds of meters of the water column. But thermodynamics dictates that heat eventually diffuses, and the global conveyor belt of ocean currents is actively transporting this thermal energy into the deep interior of the planet. When the temperature of the deep ocean rises by even a fraction of a degree, the immediate physiological consequence for an ectothermic giant is catastrophic. Unlike warm-blooded mammals that can regulate their internal temperatures, a cold-blooded deep-sea creature is completely at the mercy of its environment. Its internal body temperature matches the surrounding water exactly. According to the Van 't Hoff rule and the principles of chemical kinetics, a rise in environmental temperature exponentially accelerates the speed of biochemical reactions within a cold-blooded organism. For every 1 degree Celsius increase in water temperature, the baseline metabolic rate of a marine ectotherm can increase by roughly 10 to 20%. For a giant isopod, a Japanese spider crab, or a colossal squid, this thermal metabolic acceleration is an economic nightmare. These creatures are built entirely for a slow-motion, low-energy economy. Their massive bodies require a tremendous amount of absolute energy simply to maintain cellular structures and prevent tissue degradation. They can only survive in a food-starved desert because their cellular engines idle at the absolute minimum threshold. When the water warms, their metabolic engines are forced to rev up. Their cells begin to burn through energy at a frantic, elevated pace. Suddenly, a giant isopod can no longer survive for 5 years without food. Its stored lipid and protein reserves are consumed within months by its accelerated metabolism. The creature is forced into a state of chronic systemic starvation. It must find substantially more food in an environment where food is already fundamentally scarce. Because the deep sea cannot magically increase its supply of falling whale carcasses or marine snow to match the accelerated appetites of these creatures, the inevitable result of ocean warming is widespread metabolic exhaustion and localized extinction events across the abyssal plain. This thermal crisis is directly compounded by the second, even more devastating future challenge: global ocean deoxygenation. As we analysed in Part 3, the deep sea is currently rich in oxygen, because cold water possesses a high physical capacity to hold dissolved gases, and polar winds fully charge these currents before they sink. But as global temperatures rise, two disastrous chemical and physical changes occur simultaneously at the polar zones where deep water masses are formed. First, as surface waters warm, their physical capacity to hold dissolved oxygen declines significantly due to the laws of gas solubility. The water literally becomes less chemically capable of trapping oxygen molecules. Second, the melting of polar ice caps and glaciers introduces a massive volume of fresh, low-density water into the polar seas. This influx of fresh water creates a severe density stratification at the surface, preventing the heavy, saline currents from properly mixing with the atmosphere and absorbing oxygen before they plummet into the abyss. The global conveyor belt is beginning to slow down, and the deep currents that move along the ocean floor are carrying significantly less dissolved oxygen than they have at any point in recent evolutionary history. This reduction in dissolved oxygen hits deep-sea giants at their point of greatest anatomical vulnerability. We must remember that a large body mass requires a highly efficient diffusion gradient to push oxygen molecules deep into thick muscles, massive organs, and complex nervous systems. Deep-sea giants were able to abandon complex energy-consuming circulatory networks and grow massive, thick tissues precisely because the surrounding water was completely saturated with oxygen, creating a steep chemical gradient that forced the gas directly into their bodies. When the concentration of dissolved oxygen in the deep water column drops, this vital chemical gradient flattens out. According to Fick's laws of diffusion, when the external gas concentration decreases, the rate at which oxygen can penetrate into an organism's tissues drops precipitously. The oxygen molecules can no longer reach the innermost core of a large animal's body. The inner cells are starved of the essential electron acceptor needed for aerobic respiration. The animal begins to suffer from internal hypoxia, a slow, systemic suffocation at the cellular level. This creates a terrifying evolutionary paradox known as the metabolic index squeeze. At the exact same time that ocean warming is forcing the animal's cells to demand more oxygen, to fuel an accelerated metabolism, ocean deoxygenation is reducing the available supply of oxygen in the water. The creature is caught in a vice between rising demand and collapsing supply. Under this intense physiological strain, the maximum sustainable body size of a species decreases drastically. Evolution will actively select against giant individuals because their massive frames are the first to suffocate under low oxygen, high temperature conditions. Across generations, the titans of the deep will be forced to undergo a process of evolutionary dwarfing, shrinking in size to survive the changing chemistry of their home, or they will simply vanish entirely from the fossil record. We must also consider how these future climate challenges disrupt the complex food webs that sustain deep-sea gigantism from above. The deep sea does not exist in isolation. It is entirely dependent on the organic matter that falls from the sunlit surface waters. Ocean warming and acidification are currently causing massive disruptions to surface ecosystems, altering the populations of phytoplankton, zooplankton, and pelagic fish. When surface productivity declines or shifts unpredictably, the volume of marine snow that drifts down into the abyss drops significantly. Furthermore, because warmer water accelerates the metabolic rates of bacteria and small scavengers throughout the entire water column, the dead organic matter that does fall from the surface is consumed and broken down much faster as it travels through the twilight zone. By the time the marine snow finally reaches the abyssal floor miles below, it has been stripped of almost all its remaining nutritional value. The continuous, low-level food pipeline that sustains the baseline survival of benthic giants is being starved out by the accelerated consumption of the upper layers of the ocean. We cannot analyze the future challenges of the deep sea without acknowledging the direct mechanical and physical threats posed by industrial human exploration, most notably deep-sea mining. The abyssal plains are rich in polymetallic nodules, golf ball-sized rocks that contain heavy concentrations of valuable minerals such as cobalt, nickel, copper and manganese, which are highly sought after by human industries for the production of electronics and green energy batteries. These nodules are formed over millions of years through the slow precipitation of metals out of seawater, and they serve as the primary solid substrate for life on the muddy sea floor. The initiation of commercial deep-sea mining involves deploying massive, multi-ton robotic vehicles that crawl across the abyssal plain, scraping up the top layers of mud to harvest these nodules. This process represents an ecological catastrophe for deep-sea giants. First, it completely destroys the physical habitat. Animals like the giant tube worm or deep-sea echinoderms rely on stable substrates to anchor their colonies or navigate the terrain. Second, the heavy mining machinery stirs up colossal, dense plumes of fine sediment that can travel through deep currents for hundreds of kilometers. These massive sediment plumes clog the delicate, fragile respiratory organs and gills of giant isopods, Japanese spider crabs, and deep-sea fish, causing immediate suffocation. Furthermore, the plumes completely obscure the faint bioluminescent light signals that giant squids and other deep-sea predators rely on to hunt and avoid danger, rendering their basketball-sized eyes completely useless in a fog of industrial mud. The extreme longevity and slow reproductive cycles of deep-sea giants make it completely impossible for their populations to recover from these industrial and climate-driven disruptions. As we analysed in Part 5, a Greenland shark takes 150 years to reach sexual maturity, and a giant crab may spend decades slowly accumulating mass between rare molting events. Their genetic code is optimized for a world where change occurs over epochs, not decades. They do not possess the capacity for rapid genetic adaptation or explosive reproductive recovery. If an industrial mining operation or a sudden deoxygenation event wipes out a population of benthic giants in an ocean basin, that lineage is gone for centuries. There are no rapid generation cycles to replace them. Thus, when we peer into the future of the deep ocean, we see that the very traits that made these creatures the ultimate masterpieces of evolutionary adaptation are now the targets of a changing global climate. Gigantism is an elite strategy for an immutable, cold, and oxygen-rich paradise. But in a warming, suffocating and industrialized ocean, being a titan becomes an unsustainable luxury. The future challenges of the abyss are not distant hypotheses. They are measurable chemical and physical transformations occurring right now beneath the waves. If humanity does not recognize its profound connection to the deep interior of our planet and take decisive action to curb global carbon emissions and restrict destructive deep-sea mining, we risk erasing the greatest, most ancient biological fortresses on Earth. The magnificent giants of the abyss who conquered the crushing forces of pressure and the endless starvation of the dark across millions of years may ultimately find their match in the rapid, careless changes originating from a world they have never even seen. Our journey down into the absolute depths of the global ocean reveals a profound truth about the nature of life on Earth. The deep-sea abyss is not a barren wasteland defined merely by its terrifying physical constraints. Instead, it is one of the most magnificent evolutionary laboratories in the biosphere. Through our scientific exploration of this dark world, we have witnessed how the traditional rules of terrestrial biology are completely turned upside down. The crushing hydrostatic pressures, the unchanging near-freezing temperatures, the rich chemical currents of polar oxygen, and the silent slow-motion economy of starvation do not limit life. Instead, they act as the ultimate architects of monumental scale. By dismantling genetic growth barriers, adapting lightweight cartilaginous and fluid-filled body frames, and extending their lifespans across centuries of undisturbed time, these creatures have transformed a hostile desert into a kingdom of titans. The giant isopod ruling the muddy plains, the Japanese spider crab striding through the dense brine, the colossal squid deciphering bioluminescence with its basketball-sized eyes, and the Greenland shark gliding through the Arctic darkness are all living monuments to biological endurance. They prove that when nature is granted absolute environmental stability and infinite time, even the simplest blueprints of life will expand to conquer the impossible. If you have enjoyed this deep scientific dive into the mysteries of abyssal gigantism, please support our ongoing research by clicking the like button and subscribing to the channel for more deep-sea expeditions. Your engagement helps us continue producing highly detailed educational science content. We want to hear from you, so please leave a comment below sharing exactly where in the world you're currently watching this documentary from and what time it is right now in your location. Thank you for watching, keep exploring the wonders of our natural world, and we'll see you in the next episode as we continue to unlock the deepest secrets of our planet.